The recording. Okay, so I'm gonna give a brief introduction. It's my pleasure to introduce Marine to you all. So Marine has done all of her, like most of her studies in Cambridge, from bachelor to master's and PhD, starting from natural sciences with a focus on physics and neurobiology, to a master of science in physics and a PhD in computational neuroscience, and now she's doing a postdoc in Stanford. And I give it to you, Marine, from here.
Nice. Yeah, thanks for the info. And yeah, thanks a lot for inviting me to present this. Um, okay, so I guess the work I'm going to present today is called like when and why does motor preparation arise in RNN models of motor control? And this was joint work with so Tatsuo and then my supervisor Guillaume Henquin. Yeah, so like again, feel free to interrupt like during the presentation if you have like questions or clarification points. Um, and um, and yeah, I'll aim for like roughly half an hour, but like if there's question throughout, I think that's fine. So just for like some background, I'm as you like probably are all very familiar with, a very current like common like experimental paradigm in like to study the control of movements is the delayed reaching task. And so in those tasks, animals, so typically like non-human primates or rodents, are taught to perform delayed reaches. And actually, can you see my cursor actually? Oh,
Yeah, we can say it.
okay, perfect. And so basically, like the way this works is the animals are shown a target, and then there's a delay period during which they know the target identity, but they're not allowed to move yet. And then there is a go queue after which the animals need to reach typically like as fast as possible to the target. And so interestingly, what has been found is that if you look at the neural activity of like monkeys during those tasks, the neurons actually like start showing kind of movement dependent changes before the onset of movement, like during the delay period. And so this kind of like activity that arises like before the movement, but seems to kind of like encode some information about the movement, is typically referred to as preparatory activity. And it's a quite consistent feature that is like often seen in like neural activity during those tasks. And one way in which like this preparatory activity has been understood has been through the lens of dynamical systems. And so there's this kind of like dynamical systems paradigm to modeling motor cortical activity. And within this paradigm, basically a way to understand preparatory activity is that there is this like preparation phase, which can be understood as kind of like seeding the dynamics of the like movement epoch activity with movement specific initial conditions. And so within this view, the idea is that preparatory activity is kind of potentially like input driven, and basically the activity is getting pushed towards a subspace from which then when the go queue comes it like evolves potentially like in an autonomous way to lead to like the correct movement. And so really like within this view the idea is that the initial condition of the movement phase then plays a really important role and it's viewed as kind of the main determinant of the subsequent activity patterns. And um, and then, like this kind of relies on the assumption that movement epoch activity might be largely autonomous. And and this view also comes from the fact that neural recordings show that like the movement epoch activity can be like pretty well captured by autonomous dynamical systems. And so this paradigm has also kind of transpired in the way in which like RNN models of motor control are often built, because those often assume that you might have like some initial input that defines the subsequent task, and then like you can train an RNN to like execute the following movement in like a somewhat autonomous way. So this is one kind of paradigm that has been kind of prevalent in understanding motor preparation. But on the other hand, there is also like evidence for the role of potentially important inputs to motor cortex during the movement phase. And in particular, there was this very nice paper that showed in rodents evidence for like inputs from thalamus to motor cortex during like the movement execution phase, which seem to be crucial for the correct execution of the movement. And so this suggests that at least in rodents, there are potentially inputs to motor cortex during the movement phase, which are also important for accurate execution. And from a modeling perspective, if you take like RNNs and you ask RNNs to perform like a delayed reaching task, so I'm going to go into the details of this model like in the next couple of slides. But the idea is that if you take an RNN and you give it inputs and then ask it to like drive some model to perform a delayed reach, uh, in terms of kind of like accuracy of the model output, the RNN can solve this task equally well if you give it inputs just during the like delay period or just during the movement phase. And so this kind of raises the question, like if there isn't kind of like clear behavioral advantages to having only like preparatory inputs, kind of is there anything like optimal about having like preparation during the execution of those movements? And the way in which we wanted to ask this question was by taking like an RNN modeling approach and asking like when and why does preparation arise in optimally controlled RNNs performing delayed reaching tasks. So to address this, we basically defined a model of an RNN, and so basically we defined a model as follows. So we assumed that we had some RNN model of M1, and we modeled it as an input-driven dynamical system, itself controlling a norm model. And so the way this looks is we basically have this network which evolves according to this kind of like vanilla RNN dynamics. And then the firing rates of the network are decoded into a set of talks. And we then use those talks to drive this like simple like two-dimensional arm model, which evolves in like according to like a simplified biophysical equations. And so importantly, in this model, we took the approach of like fixing the parameters of the model, so the parameters of the dynamics W, this readout C and this baseline input H. And we performed like the optimization to solve the delayed reaching task in the space of inputs. And we basically optimize the inputs for each movement to solve a delayed reaching task. And so I'll describe in the next slide like how we define like the cost for this. But basically, one thing you'll notice is that in this equation, we have essentially like potentially time-dependent inputs. And so what we did is we kind of like assumed like the system is fixed, and we wanted to see what sort of like temporal or like spatio-temporal distribution of inputs would give rise to like kind of the optimal solution when asking the model to like perform this task. And so I said we fixed those three parameters like W, C, and H. And for most of the results I'll show, we fixed W here to be this inhibition stabilized network. And so this connectivity comes from this paper like from 2014. And this is basically a network which has like pretty like strong dynamics. And it's kind of been shown that the activity of that network shows like resemblance to the dynamics of motor cortex, which kind of justified us like choosing it as a kind of model of M1. And then for this kind of like baseline input, we defined it to be this like condition independent baseline, and we just fixed its value so that we would have baseline firing rates of about like 5 Hertz for each neuron. And then for the readout from rates to talks, we defined this to be like a random matrix. And so this is kind of the model we set out. And so as I said, like really like in this case, what's going to determine like the evolution of the network is this set of control inputs U. And so what we did is we then optimized these control inputs such as to minimize a cost function that tried to capture like the features of the delayed reaching task. And so we defined the cost function as follows. Uh, so so we had like three main terms in the cost. And so the first one was this target term. Uh, and so basically this is a cost that was active like basically, so we basically defined our cost of like a time period that contains this like delay period and then movement phase. And the target cost was active from the onset of the go queue. And we included this kind of like temporal scaling to encourage the target to be acquired as fast as possible. And so this is a cost that basically penalizes how far the arm, um, so like the arm coordinates are from the target. And so this term is going to be different for each target we're optimizing for. And then, because we were modeling these delayed features, we also had this null space cost. And basically, this was a term that was active only during the delay period. And what this acted as was to penalize basically any movement of like the output of the model, so either torques or like arm velocity or arm position during the delay period. And so this was capturing the fact that during those delayed reaching tasks, animals are typically like they're not allowed to move during the delay period, and the task fails if they do. And finally, like so, this was capturing kind of like the standard like task requirements, and we also had this kind of control effort cost, and so this was basically active like throughout the whole time course of the task, and this was essentially an L2 penalty on the inputs, and so one way to understand it is that this is kind of like penalizing how much input energy is being used to solve the task. So it's essentially constraining the inputs to remain small. And it could be interpreted as some sort of like potentially like a metabolic cost of like not wanting to have like very, very large activity patterns. And then more practically, this is also like a kind of like a regularization term, which is necessary if we want to like solve this task. Um, and, um, and so we define this cost function. And we had like basically these hyperparameters here in the cost, like how much we weigh each term relative to the other. And the way in which we chose these parameters was by basically doing like a hyperparameter search of the values of alpha null and alpha effort, and finding parameters for which the task was like accurately solved by the model. And so basically this meant that for these parameter values we chose, the model was able to not move at all during the preparation phase and then accurately reach to the target. So then like this was the cost function we wanted to optimize. And so this like is a function of only the inputs to the network because those like determine the whole behavior of the model. And so this is an optimization of a time series of inputs. And so this is like a nonlinear control problem because we have nonlinearities in the dynamics. In like the main nonlinearity being like in the arm model, which has like pretty nonlinear dynamics. And so to find the inputs, we used the ILQR algorithm, which is kind of well suited to solving these like control problems in nonlinear dynamical systems. Um, okay, so just to check, is there any questions or do things make sense for now?
We are good, I think. Let's go.
Okay,
Yeah.
okay. Okay, so this was the setting. And basically, what we were interested in is seeing, like, once we've like set this up, what are the optimal inputs for the task going to look like? And in particular, we were wondering, like, are we going to get like a lot of preparatory inputs? Like, what sort of like control strategy is the model going to use? And in particular, like it wasn't completely like it's not completely obvious that it's advantageous for the model to use inputs during the delay period here because we have this null space constraint. And so basically, if you give inputs to the model like very early on, these need to like kind of like be constrained so that the activity like remains in the null space of the output. And so this like makes the delay period inputs kind of like it's like a little bit more challenging to give inputs during that period. And so it's not clear why you would necessarily get inputs emerging at that point. But what we found is that when we perform the optimization, the inputs optimized for the task arose so both like during the movement phase, but also during the delay period phase. And so here I'm showing you, so this is like for one example movement, and basically we see like we get quite a lot of like inputs before the start of the movement, and these give rise to like changes in the firing rates, as you would expect from the dynamics. But these changes aren't reflected in the behavior. And so this is like what we would expect because the network is forced to like not move during the delay period. Um, but um, but so then like we were wondering like okay, so more quantitatively like how much does the network rely on preparation versus on like these movement inputs? And so to address this, we defined this preparation index, which was a way to basically quantify, how much does the network rely on preparatory inputs. And so this is basically the ratio of the amount of inputs during like the delay period. We call this delay period delta prep. And this is the ratio to these inputs to the inputs during the movement period. And what we found is that if we look at different settings of the tasks in which we kind of like gradually like increase the delay period, we see that the preparation index kind of like increases as like the delay period increases, and then it starts plateauing after about 300 milliseconds. So in this plot, like it makes sense that when there is no delay period, like the preparation index has to like be at zero. But then basically what this suggests is that then as we start allowing the network to potentially prepare, it starts making use of that preparation phase up until a point after which it seems that having like more potential preparation time doesn't really seem to help anymore. And this is
Marie, can I just ask a quick question about that?
yeah.
Looking at the preparation index, it looks like an integral, a sum over the preparation time. So doesn't it have to be that as the preparation time gets longer, the preparation index would get higher?
No, it does. So like it makes sense that, well, I guess like it does if the network is kind of like using the like I guess it does if the optimal solution relies on giving like inputs like all throughout the preparation period.
I mean,
Uh,
imagine during the preparation period, the inputs are just random. You'd still
yeah,
get variability, and the longer the time period, the more that numerator of the index would increase, no?
yeah. So yeah, that's true. But actually, if you were giving just random inputs during the preparation period, you would
Yeah.
expect basically like a scaling, like a linear scaling, I guess. Oh, I guess yeah, because we have like a square root. Yeah, we would expect basically like a square root, like
Yeah.
with time, like with preparation time. Well,
Right.
here instead we kind of see this like plateau where I guess like initially you get more and more inputs kind of like occupying this preparation period, and then the amount of inputs kind of stops plateauing even though like this integral is performed over a longer time period.
Mhm. Okay, thank you.
But yeah, it's true that like in theory, like if you were giving random inputs, you would definitely expect an increase of this with delta prep, but actually you would expect a bigger increase than what we see for like longer times. Um, And so here, so here the idea that the network initially makes use of the preparation period and then it stops helping as much. And this is also reflected if we look at the total cost. Um, so the total cost like initially kind of like decreases as the preparation period increases, and then it also like starts plateauing after like a certain value of the delay period. And actually, like this decrease in the total cost was kind of interesting to us because it suggests that essentially the total cost to solve the task is lower if the network is essentially allowed this delay period. And what we can see is that this decrease is driven, so in part by a decrease in the target term. And so this seems to come from the fact that when the network is allowed to prepare, it can then perform the movement like it can have sort of like slightly lower reaction time, which allows to reach the target faster, which leads to this like decrease in the target cost. But interestingly, we also see like a small decrease in the kind of control effort cost. And this was like initially kind of counterintuitive to us because like actually, as you just said, like basically if we increase the delay period, we're increasing the kind of time over which the inputs are integrated. And so we're kind of like summing over more inputs. And so you would expect that if you're summing over more inputs, like that's going to lead to like an increase in the total like cost of the inputs. But actually, like when kind of preparation is allowed, the network is able to solve the task with like smaller inputs. And so then this leads to like an overall smaller control cost. And then,
If it's
yeah,
okay.
is it, did you have a question? Or?
Yeah. My question is, maybe I lost that and you explained that already, but do you have any delays in the model? Like in reality, there's like at least 70 milliseconds, 100 milliseconds delay between the visual information arrives at the primary motor cortex, for example.
Yeah, no, so here there are no delays. And so actually, yeah, like that's a good point. So actually one way to kind of like understand the like so here we haven't incorporated delays. So when you look at like these numbers for like delay period, it might make sense to think of it as like you could like add some sort of like internal like delay period that would capture like those internal delays. So here like we have the Go queue, but actually like this would be more some sort of like internal Go queue that might come in like slightly later than the external Go queue if you were accounting for those delays. So here, yeah, all of this is without delays.
You're saying that this delay here is because the internal state of the RNN should reach a specific high number for the muscles to actually generate something. And that's why it's beneficial for the RNN to have the target information earlier, right?
What do you mean? Sorry.
I mean, you said like an internal delay, and that internal delay comes from the fact that the RNN hidden activity should increase to a sufficient value for it to generate muscle activity. That's why it has delay.
So what I meant with the internal delay was just something like, okay, so I guess what I meant is like we don't have any kind of like delays in like visual processing or like sensory processing in the model. And so basically like when we talk about the Go queue here, this is the Go queue that's like kind of immediately being processed by the RNN. And so if you wanted to like I think a more realistic model would incorporate kind of like internal like sensory delays, in which case this Go queue would actually never be able to be at like 0 seconds, but you would always have like some sort of like window that would also account for like sensory delays. So all I'm saying is that this Go queue here, like I think of it more as like some internal Go queue of like this is the point at which the information is getting kind of like processed in motor cortex, and then from which the activity evolves. But yeah, I don't know if that really
Yeah.
addresses.
We can continue. Yeah, thanks.
Hey, can I ask another quick question? Why do you see an increase in the null loss function with bigger preparation time?
Yeah, so yeah, that's a good point. So basically, this reflects the fact that as you have longer and longer delays, it becomes harder and harder for the network not to move at all during the delay period. And so basically it becomes harder to like stay in the null space for like a very large amount of time, which leads to this kind of like increase in the null space cost. But again, so here we had like some threshold, like when we set the hyperparameters, we kind of ensured that like the movement during the delay period was always small enough that we would consider it as like basically not moving. And so even though we see this increase here, like all of these tasks were still kind of like accurately solved with the arm like not moving like a lot, like basically like not moving, but maybe like having like small like jitters of the hand position. But yeah, this reflects the fact that it's harder to stay in the null space for like very long delays. Yeah. Does that make sense?
Yes. Yes.
Okay, nice.
Continue, yeah.
Okay. So basically, like here, yeah, we see like the cost also decreases a function of the delay period. And we see like this plateauing behavior. And so then to understand the kind of plateauing behavior, we looked at what the kind of like inputs and the firing rates looked like in the model for different amounts of delay period. And what we found is that as we kind of increase the delay period, like the inputs kind of like starts like coming in during the delay period, but they don't come in a uniform way like throughout the whole delay period, but instead they tend to come in like mainly like right before the go queue. And so this kind of translates into like the network activity like after 300 milliseconds starts looking like very stereotypical. So basically after like about 300 milliseconds, we don't really see any difference in like what the network activity looks like during the movement phase. And what we find is that basically, like these inputs are always coming in very late, right before the go queue. And the reason for that is that actually, like in our model, we have this like vanilla RNN dynamics, and so inputs given too early kind of are more easily like forgotten by the network. So it can't like in this setting, it's not trivial to like keep the inputs like in the memory of the network, and so the network tends to rely on this like kind of just-in-time strategy in which it gives inputs like right before the movement is going to start. And one thing to note is that here, this is kind of a strategy that makes sense for the network because it knows the delay period in advance. And so, so it can, like, it is possible to give the inputs like right before the go queue is going to come in. But this is kind of different if you, like, in real experiments, often the delay period is random. And so in that setting, like if we had like a random delay, it might make sense to kind of prepare as early as possible so as to be ready when the movement starts.
Sorry, I
But
have one quick
yeah.
question here. So these different networks with different preparatory delays, are these trained separately, you mean?
Yeah, so basically here we have one network, and for each setting of the task, so each delay period, we optimize the inputs.
Uh-huh.
So yeah, so the inputs here are all found like separately.
Okay.
Yeah, and one thing to note is that so when we optimize the inputs, it's like there isn't a unique solution to the inputs, but we actually find that like the time courses of the inputs are like kind of very consistent, and yeah, so like even though there isn't like any guarantees of finding like a kind of global optimum, like these results are kind of robust to like the initialization of the inputs.
Just one more quick question. What's the dimensionality of these inputs? Like, what's the nature?
Yeah.
Like, I see this like high peak for the green one, for example, but the others are not like that. Like, yeah, what's the nature of the inputs?
Yeah, that's a good question. So the network has 200 units, and here the inputs, we give one input to each unit of the network. So this is 200 dimensional. And here, I mean, I'm only showing like, I think 10 of them here, which I picked like randomly. And yeah, it's true that like the green one is much bigger, but in general, like this kind of, yeah, like a lot of them exhibit like, kind of like a burst in activity right at the beginning of the movement. But yeah, like some of them, like it's definitely, so the inputs themselves, like there is no constraint that forces any dimension, like they're kind of like a priori isotropic. But I guess like because the connectivity itself has like structure, then like the inputs end up having like different input channels end up having like a different impact on the dynamics.
Perfect, thanks.
Okay, so yeah, so basically like this kind of explains why we see this plateau in the preparation index after 300 milliseconds. And then what we were wondering there is like, we see that this ISN relies on preparation like up to a certain points, but like why exactly like is it advantageous to have like these preparatory inputs? And like more generally, like what is kind of the interplay between the dynamics of a network and like how much it's going to rely on preparation? And so to address this, like we first did a pretty like crude analysis where we just looked at like what the inputs and like the optimal control strategy would look like for different choices of this W matrix here, so different connectivity choices. And so here I'm showing you examples in like 5 different networks. And so even like visually, we see that like with different connectivities, we actually get very different control strategies. And so for instance, like the first network we looked at was this unconnected network. And so basically, this is a network where W is set to be 0. And we see like here the eigenvalues are all at 0. So, and so in this network, the network has basically no dynamics. And so in this network, there is kind of like no advantage to giving inputs during the preparation period, because those inputs are going to be completely forgotten by the network. And those inputs like also can't like aren't allowed to have any like direct motor output during the preparation phase. And so in this case, like the optimal strategy is to not give any inputs during preparation and to give only movement inputs. And so this is kind of consistent with the intuition that if the early inputs are going to be completely forgotten and can't be like somehow like kept inside the dynamic, then there is no point in giving them. And so then we looked at a network with a random connectivity. And so this network actually has like some dynamics. It has like actually like pretty like slow time scales in its dynamics. But interestingly, we found that this random network actually didn't rely on preparation much either. So here, I mean, it might be a little bit hard to see, but like there's like very like little inputs during preparation, and most of them come during the movement period. And interestingly, on the other hand, if we look at an oscillatory network, so this is a network where like all the eigenvalues have the same decay time scale, but we have a bunch of like rotational modes. And actually, this network exhibits like quite a bit more preparation than the random network. And so it seems that like for some reason, like oscillatory dynamics kind of like that like preparation is kind of encouraged when we have these oscillatory dynamics. And interestingly, if we look at like this is now the ISN, so this is the network I've been showing you before. And if we look at its spectrum, it has quite a lot of oscillatory eigenvalues actually. So part of the reason why the ISN might rely so much on preparation might be because it has like all these rotational modes. But the other thing that the ISN has is it has like quite high non-normality. And so this means basically that like the connectivity matrix is non-normal, so it has like it satisfies this equation. And what happens with non-normal dynamics is that you can get kind of amplification of the inputs. And here we wanted to kind of assess like how much the non-normality played a role in the ISN relaying and preparation. And so to assess this, we also generated a surrogate ISN, which was basically this ISN, but to which we applied a similarity transformation, so that it would have the same eigenvalues as the ISN, but no non-normality. And what we found is that if we kind of like quantify like the prep index of these different networks, the surrogate ISN actually prepares like relies quite a lot less on preparation than the full ISN. And it kind of prepares like about as much as an oscillatory network. And so what this suggests is that like basically from this kind of cost analysis, we see that the amount of preparations that networks display is going to depend a lot on the actual like dynamics of the network. And so at this point, like we wanted to get kind of like a better understanding of the interplay of dynamics and inputs, and kind of like a more like quantitative analysis. And so what we did is we tend to kind of like simplified two-dimensional models of the model I've just shown you, and we basically simplified the dynamics to be two-dimensional and linear. And we assumed that the output was now a linear readout into a one-dimensional space. So this captures some of the features of the task in the sense that we have like a null space in the task, and we have like this dynamical system driving an output, and then we defined a cost of the output that was similar to our delayed reaching task. But the advantage of this formulation is that because we have a two-dimensional network, we were able to kind of like parametrically like vary the dynamics and look at how preparation depended on like the exact parameterization of W. And here, like in particular, because of what we had seen, we were kind of interested in investigating like two types of dynamical motifs, which were like non-normal dynamics and oscillatory dynamics. And so what we did is we defined two-dimensional like non-normal systems which had this connectivity. And basically, with this connectivity, what you have is so this parameterizes like a non-normal system, and basically the system has two modes. And so the first mode, so here this would be like this orange mode, is essentially like a source mode in the dynamics. And the brown mode is kind of like a sink mode. And what this means is that basically when you apply this connectivity matrix to the system, it's going to multiply the activity of the source mode by W and feed it into the sink mode. And so what this means is that there's like this asymmetry in the dynamics because essentially like the two modes play like very different roles. And what we found is that if we look at how much like a model like this relies on preparation, the amount of like preparation it displays actually depends a lot on which of the modes we are reading out. So which of the modes is read out into the output space. And so here I'm showing two extreme examples. So one in which we read out from the sync mode, and we see that the network relies quite a bit on preparation. And the other one we read out from the source mode, and it doesn't prepare at all. And this kind of makes sense because here basically the dynamics are getting, so depending on the value of W, they're getting like more or less amplified from the source to the sync mode. But basically, if we're reading out from the sync mode, there is actually an advantage to giving like preparatory inputs because those inputs can then be amplified and like later on be read out into the relevant subspace, which is in this case the sync mode. On the other hand, if we're like reading out from the source mode, there's kind of no point in giving early inputs because those would be directly like basically there is no point in giving any inputs early to the sync mode because those would get completely lost and have no effect on behavior later on. And it's kind of not allowed to give inputs to the source mode because the network is constrained not to move during this early phase. And so this is for non-normal dynamics, and then for oscillatory dynamics, actually, like these are completely symmetric. And what we find is that in oscillatory systems, we always see like quite a bit of preparatory inputs. And here, like one kind of intuition for why we would see these inputs is that basically because we have these rotations, if we can elicit some activity kind of like early on along one of these modes, the activity is then going to be rotated into the other subspace later on. And so then it is possible, like if this is like the mode we don't want to read out from during preparation, we can give inputs along this mode, and then they're going to be rotated to be in the like output space at preparation time. And so this suggests that there is kind of like and like the interplay of like kind of the null space and the dynamics plays an important role in determining how much networks are actually going to prepare. And so like we kind of like quantify this a little bit more by computing the preparation index for these different networks for different values of W and different alignments with the readout. And so as expected, the readout doesn't play a role for these symmetric oscillatory networks, but it's actually like very important in non-normal networks. And in both settings, we see that as we increase the non-normality, we initially get on the oscillations, we get quite a big increase in like how much the networks prepare. And then at some point, we see this plateau. And one reason for this plateau is that basically, like as you increase W, the dynamics are getting stronger and stronger. And so that means that you can get kind of like more and more use of the preparation phase, but it also makes it harder and harder to kind of remain in the null space during preparation. And so there is kind of this trade-off, which I believe leads to this plateau emerging. And so like basically like this gives a sense of like the fact that preparation depends on the interplay of readout and dynamics. And so we wanted to get a bit more of like a quantitative sense of this. And I'm not going to go into like the details of this, but basically we try to quantify these notions of alignment of readout and dynamics like a bit more precisely using kind of ideas from control theory. And so here I'll just give the kind of high-level overview, and then I'm happy to discuss after. I'm quite close to the end now. But basically what we found is that like you can kind of summarize the main ideas that are going to predict preparation as follows. So preparation is going to be advantageous if you can have null space inputs that can then get amplified into the readout at movement time. And on the other hand, preparation will be less useful if you have a network that is very easy to like steer in the readout space, because at that point it means that it's also kind of hard to keep it like in the null space during preparation. And so in that case, it's actually like potentially easier to just rely on movement inputs. And so these ideas can be summarized using ideas from control theory, which is like the observability of the null space and the controllability of the readout. And what we found is that if we kind of take these like two metrics, which are like kind of like two scalar values that summarize like these properties of networks, we could actually like decently well predict like how well, like how much networks would rely on preparation. And so, I mean, like potentially a lot more to the story, but these kind of simple properties of the network seem to give like a decent predictive model of how much networks will prepare. So this was kind of like us trying to address the question of like when and why like networks will rely on this preparation phase. And now in the last like couple of minutes, I just want to discuss like one last kind of experiment we did with our model, where we wanted to look at how like the optimal strategy found by the model compared to like findings in experiments. And so in particular, we wanted to compare to this like sequential reaching task that was performed by Andrew Dimnick and Mark Churchland. And so the thing is, in our analysis so far, like we've looked a lot at this preparation index, but this relies on having access to the inputs to the network. But in experimental data, we typically like don't have access to the inputs. And so instead, we used this metric that was proposed in this paper, where we defined basically the preparatory on movement subspaces. So we defined subspaces like using the like neural activity traces. And these subspaces are basically the ones that capture most variance during respectively the preparation phase or the movement phase. And once we've defined those, we can look at the occupancy of the subspaces across time, so how much variance they capture across movements. And this gives us a metric that we can compute both in the model and that has been computed in these experiments. And so we can kind of compare the preparation strategy of the model to the ones seen in monkeys. And so, as I said, we were interested in modeling this like sequential reaching task. And so this was a task that I'm guessing some of you are probably familiar with, but basically like the first trained monkeys to perform like double reaches. And so they had two settings. There was a delayed double reach with a compound reach. And in both settings, they showed the monkeys two targets at the beginning of the task. And then there was a delay period. Then the monkeys had to reach to the first target. And in the first setting, there was then another delay period after which they had to reach the second target. And then in the compound settings, they actually had to like reach the first target, acquire the target, so pause briefly on it, and then move to the second target. And so the question the authors had there was, in this setting, given that the monkeys know both targets like from the beginning of the task, are they going to prepare like once for the whole like movement sequence, or are they going to rely on like kind of two preparation phases, one for each movement? And what they found, which was kind of surprising, especially for this compound reach in which you can kind of view the sequence as like a single compound movement. But what they found is that actually the monkeys exhibited like occupancy of the preparation subspace twice during the task, which suggested that they were kind of going back to this preparation subspace before each movement and not just preparing once like for the whole sequence. And when we kind of modeled the same task with our model, we found that in the model, instead of having kind of one main preparation period, like the optimal control strategy was kind of similarly to rely on kind of multiple preparation periods. And so if we look at the input, this kind of translated in just having like kind of a burst of like inputs to the network right before each movement. And interestingly, like you might expect this for the double reach, but it was a bit more surprising in the compound reach, given that there's kind of no explicit pose in the model again. And so yeah, here basically like the model exhibited this kind of like similar behavior of having like a double like preparatory occupancy rather than having like a single peak. And in the model, actually, like we can kind of get some intuition for why that happens, because so I think what's happening in the model is basically that because you have these two movements and because you need to like pause on the target, our model is kind of forced to like slow down and like acquire the target, so like there's like a deceleration, and then to reaccelerate, we kind of need to like have this like new influx of energy into the network, which takes the form of this like new bursts of like inputs basically. So yeah, so basically, yeah, this was like everything. So just in summary, yeah, we investigated like when and why preparation occurs in optimally controlled RNNs performing fast delayed reaches. And we found that preparation is most advantageous in networks with like strong dynamics, which can amplify early inputs into later motor signals. And interestingly, the networks that prepared the most was those that most closely actually like resemble motor cortical activity. So those ISNs like have dynamics which kind of look quite a bit like motor cortex, and they're also the ones that rely most on preparation. And finally, we found that yeah, like the optimal control of sequences of features involves like kind of multiple periods of preparation, which seems consistent with some recent data. Okay, so yeah, now I think I'm done. So yeah, I'm happy to take questions. Also, I think I can stay for about 10 more minutes. Like it's so because
Okay.
I think the defense is in the room next door, so it's okay.
Okay, perfect. Thank you. Thank you. Hey, we can have questions from the people in the Zoom if there are any.
I have questions.
Okay, you will start.
Okay, thank you. Great talk. I have one clarification question for the sequence simulations, like a few slides before.
Yeah.
In their paper, because they also train R and then they hide the targets after the go queue for the compound reach. I was wondering if you're doing the same thing also, meaning that the controller knows the targets during the preparation phase, and then once the go queue comes in the compound, do you also hide the targets?
Yeah, no, so I guess like we have like a slightly different optimization paradigm here. And the way in which we like find the inputs is by kind of like optimizing this cost function. And the cost function contains both targets. And so we have kind of no way of like hiding the target. So in our setting, actually, like the model always knows about both targets, like from the start and all throughout. So yeah, we don't have exactly like the same setting.
That's great, thank you. And first of all, I also wanted to thank you for the simple model simulations. They're like giving me a lot of good insights, the simple models. And that was very nice. But the way that I understand it, the non-normality closely connects to how much knowledge space is available inside that RNN. Is that true?
Yeah, so I guess the non-normality, so I mean, in those 2D models, it's kind of an extreme case, I guess, because so in the 2D models, I guess because you only have two dimensions, it's like half of the space is the null space. But so I guess what the non-normality says is like in this case, inputs from one direction are going to get kind of like amplified into the other direction. And how aligned the null space is to the directions that can get amplified is going to really like very directly control how much it's advantageous to prepare. Because basically, if you can be like in this setting, if you give inputs like during preparation along this orange mode, that's actually like ideal because those inputs are then going to be amplified by the dynamics and then move to the readout space.
Yeah, that's the next part of it. But because you have only one readout, if you apply input to that readout, that would be catastrophic, right? Because you have it.
Yeah, and actually we kind of see it in the and actually like yeah, if we were like just reading out from the so that's why we see no inputs if we're reading out from the source mode, and that's why we also see actually that like even when we are reading out from like the sync mode, we also see that some inputs have to be given along the readout during preparation to kind of like compensate for like whatever activity has already started moving towards. Yeah.
Yeah, I was just wondering if I can transfer that intuition to a larger network. Do you think in a large, like with many, many units now, non-normality also transfers to how much knowledge space you have available there?
So I guess like some of the insights translate just from like, so we found that I guess if you're trying to predict preparation, you can kind of recap it using this like alpha and beta. And I think we found that in like high D networks, you kind of have like basically in high D networks, you can predict from like just these two things, like the kind of contrariability and observability, like the whole space, like how much the network will prepare. One thing though is that in high D networks, like if you have a very small null space, like you're going to see a lot less. Like I guess the effects are going to be like dramatically amplified in like small networks. So I think the effect that's going to dominate in high dimensions is more like just the non-normality by itself, like how much can you amplify early inputs. But it's going to be way easier to like stay in the null space if the null space is like 2-dimensional and the network is like 200-dimensional. But I think the insights do translate. Like that's yeah.
Yeah,
I
that,
think.
that was my like curiosity around here, because if it's just about the null space, then it's kind of null space is the necessity for planning, right? Because if you don't have a null space at all, there's no way for you to plan without leaking that into behavior.
Yeah.
So in that sense, I was thinking that maybe the question that is we don't still know is what is the sufficient condition here? Like given within the same networks that they have the exact same amount of potential for planning, that would be same amount of null space. What makes a network to plan more or less? Do you have any intuition on that?
Yeah, so I think that's where, yeah, no, so I completely agree that yeah, the null space is a requirement to get any planning. And I think here, like the insights we got was like the network is going to prepare more if if it has this ability to kind of like amplify early activity patterns into later activity patterns. So it's kind of this idea that like you have like if you have like kind of strong dynamics, like preparation is going to be useful if you can kind of like exploit the strong dynamics so that you don't have to like exert too much energy early on, but then you really make use of like the network dynamics themselves. So yeah, and non-normality kind of helps with that because it kind of is associated a little bit with being able to like amplify input patterns into other activity patterns.
Thank you.
I guess Paul has a question.
Yeah, thank you. Thanks, Maureen. That was really cool. I have a question about, I don't know what the answer is, but that's why I'm asking, I guess. Are there conditions where preparing before movement would be a bad idea? I mean, I like the idea that the preparation sets up this dynamical system so it can just unfold without energy, right? Are there situations where it would be a bad idea to set up a sort of automatic unfolding in that way? And are there experiments or simulations we could do to explore that?
Yeah, I mean, I could imagine, so like outside of the model, I could imagine that if like
This
I
is
guess I feel
like
like
when
the
you have to
unfolding makes
change,
sense.
when you have
Sorry?
to modify an ongoing movement.
Yeah,
It's probably
exactly.
not a good idea to have an automatic unfolding.
Yeah, I think it probably makes sense if like, because I guess it's kind of like, if you had just preparation, it would be some sort of like open loop control during the
Yeah,
movement. And
yeah,
then that makes sense if you have a perfect model of what's going to happen. But
yeah,
then I guess if you know that like I guess the more perturbations and the more like potential changes in the trajectory you expect, I guess probably the least
yeah.
useful.
I guess it's possible that you could set up that preparatory activity in a way that not only unfolds a movement, but also unfolds a movement in the context of expecting a certain kind of perturbation, right? There's probably enough null space dimensionality to have that level of extra preparation. That would
Yeah,
be,
definitely. Actually, that
yeah.
would be interesting. Yeah, yeah.
Okay.
You could imagine that you want to like, yeah, have like some subspace in which you have like information that you want fields to unfold in some way,
Yeah.
but
Thinking of
keep
like
your.
a tennis player who's about to receive a serve, and she knows that the opponent tends to hit serve towards the forehand more than the backhand, but there's still some uncertainty, and you might want to prepare a set of unfolding movements, but a specific set of them. Yeah. Okay,
Yeah,
thank you.
interesting.
Perfect. We have maybe time for one more question, quick question. If not, we can finish it here.
I can ask a quick
Okay,
question.
quick.
Hopefully that's a quick one. I was wondering, what do you think about the nature of the optimizer you used here right now? Because now we have a optimal controller controlling the dynamical system of M1. So eventually that controller should be also be implemented by another RNN in the brain.
Yeah.
So I was wondering that how do you think planning transfers there? How does this upper network knows about the condition and how the lower networks working there?
Yeah, no, that's a great question. Yeah, so here we have kind of like almost no constraints on the inputs. But yeah, I agree. In practice, I guess this would potentially come from like higher areas. And I could imagine some networks which are able to just like, I guess I could imagine a system where you have like some higher order RNN where like it just takes in some potentially like context input type of thing and is able to output this like more complex signal to M1. I mean, I think it's kind of like I guess at some point one of the inputs that comes in is the like sensory input, and then the question is how this gets translated in this like more complicated control plan. And I think I mean I don't have like a good answer on like what that should actually look like. This kind of something we like avoided here because then it becomes kind of hard to think about what constraints you should impose or like what things should exactly look like. So here the question was more like, if you give infinite flexibility to the inputs, like what sort of thing will they look like? But that also means that a lot of the features of the inputs aren't like biologically realistic, and you might expect that they have like way more structure, or, like lower dimension and things like that, if they're coming from higher areas. Basically don't have a great question. It's hard to, I know that people are working on like multi-area models like that, where you try to do some like meta learning to learn like a meta controller, which I think kind of makes sense. Like you want to like, you could try to learn some network, which is then able to like learn give you the right inputs for given context. But
Thank you very much.
Okay, thank you for your time. And yeah, I guess that's it.
Thanks a lot for inviting me and for the discussion.
Thank you for your presentation.
Yeah,
Thank you,
And
Have a great day.
I
Bye.
enjoy reading your reading list every week. Actually, I get the email.
Thank you. Bye bye.
Have a great
Okay.